Hi, I'm Dr. Gareth Moore from RP Photonics, and welcome to this RP Fiber Power tutorial series. Today I'm going to show you how simple to use, yet powerful, our fiber simulation software is. Let's dive right in with a case study which you can find on our website. Here we'll investigate how supercontinuum generation works in a passive single-mode germanosilicate fiber. We want to explore different wavelengths in different dispersion regimes. First, in the anomalous regime, in the zero dispersion regime, and in the normal dispersion regime. The goal is to come out with a better understanding of how these parameters and some nonlinear effects influence the outcome of the supercontinuum generation. Let's dive right in with RP Fiber Power. For this simulation, we use the power form titled Passive Fiber for Ultrashort Pulses. We'll begin by setting the properties of the fiber before addressing the pulse. The fiber will be set up similar to the Corning's SMF28 single-mode fiber, widely used in telecommunications. We'll set the fiber length to 1 meter and the longitudinal steps to 1000. This ensures that we resolve the quite violent processes involved in supercontinuum generation into a core radius of 4.1 microns, and we'll define the fiber by its germanosilicate doping profile. The germanium dioxide concentration in the cladding is 0%, while the core has a 3% doping concentration. We'll also specify that we want to propagate the fundamental LP01 mode. The software automatically calculates the refractive index profile from the germania doping profile, giving properties like the effective refractive index at any wavelength and the fiber's full chromatic dispersion profile. We set the nonlinear index to 30 times 10 to the negative 21 square meters per watt, a self-steepening factor, and a delayed nonlinear response for fused silica. This may not be extremely accurate given the 3% germanium dioxide, but is sufficient for this experiment. Lastly, since the pulse spectrum may broaden into the spectral region beyond 2 microns, we need to include the absorption that is usually found there. In the additional definition section of the power form, we can define a function, starting with the infrared absorption and adding propagation losses from Rayleigh scattering. Sum these into a wavelength dependent function and place it into the fiber losses section, making sure the correct units are used. We now need to find an interesting wavelength for our input pulse. Looking at the dispersion profile, our plan is to try the region with strong anomalous dispersion, 1550 and 1350 nanometers. Zero dispersion at 1313 nanometers, and strong normal dispersion at 1000 nanometers. Let's start in the Telecom C band at 1550 nanometers with a pulse energy of 1 nanojoule and a Gaussian shape with a duration of 100 femtoseconds. We also add quantum noise to the input pulse, which is important because significant parametric gain could amplify quantum fluctuations to macroscopic levels. Next, we set up the time trace. The simulation pulse grid width is set to 25 picoseconds, much longer than the pulse itself, so that we can catch the pulse spread in the time domain. Now that our system is set up, we can select our output diagrams, with the most interesting being the evolution of spectral shape diagram. Now we are ready to run the simulation. We can now see that at a peak power of around 12 kilowatts, we already get substantial spectral broadening. Next, let's increase the input energy to 3 nanojoules and see how this changes the output spectrum. We see not only more broadening towards the longer wavelength side, but also a new spectral component around 943 nanometers. This may seem like a numerical artifact, but it is a real phenomenon. Let's find out. To find which effect the spectral component comes from, we can turn off some of the different effects. Let's try the delayed nonlinear response and self-steepening. This flexibility is one of the great advantages of using numerical simulations. It's still there. Let's break down the processes involved. The 943 nanometer component comes from 4-wave mixing, a relatively simple nonlinear phenomenon that requires only the Kerr effect and is influenced by chromatic dispersion. But we don't see the expected long wavelength component. That falls into the region where it is strongly absorbed. In the simplified simulation, without Raman scattering, we see something similar to high-order soliton dynamics, strong quasi-periodic spectral breathing. where there is broadening followed by spectral contraction. The 943 nanometer component appears only when the spectrum broadens into this region, but then escapes the contraction. Let's look at the spectrogram of the full simulation to find out why. In this view, we see that the 943 nanometer component has completely drifted away from the others. This happens because the group velocity in this spectral region is much lower than that of the longer wavelength components, meaning it no longer interacts with them. Next, let's increase the input power to 5 nanojoules and observe the changes. Now, we observe significant spectral content below the zero dispersion wavelength, entering the normal dispersion range. The output also has a roughly parabolic shape. This is because different spectral components have different group velocities, with the zero dispersion wavelength having the highest. We also see some blobs, indicating soliton pulses. These are separated enough so that they propagate as more or less independent pulses. The temporal evolution shows how different parts drift apart because of different group velocities. A feature that stands out is a line that has a changing slope. This is a soliton undergoing a soliton self-frequency shift due to Raman scattering, which gradually decreases its group velocity. Looking at the spectrum, we get an octave-spanning spectrum, at least on the log scale. We also see that a much shorter fiber would actually be enough to obtain strong spectral broadening. We now move on to a 1350 nanometer input pulse, which is much closer to the zero dispersion wavelength of 1313 nanometers. We are still in the regime of anomalous dispersion, but is much weaker. This means a lower soliton pulse energy for a given pulse duration. This should also mean that the input pulse energy can be split into a larger number of solitons. The spectrogram again follows a parabolic dispersion curve, showing a broad spectral output and slightly less temporal broadening than the 1550 nanometer pulse, but overall no significant qualitative difference. Next, we set our input pulse energy to exactly the zero dispersion wavelength of 1313 nanometers. We see even less spectral broadening, because the temporal broadening is not reduced as we may have expected. Light with a large spectral bandwidth can obviously not escape the higher order dispersion. Finally, we see what happens injecting a 1000 nanometer pulse, well within the normal dispersion regime, even though this fiber would technically no longer be single mode here. Using 5 nanojoule input energy, the result is quite different from those in the anomalous dispersion regime. The spectral broadening is smooth, but much weaker. The temporal spread is also smooth and symmetric, and the spectrogram shows a strongly upchirped output pulse. It's interesting that we get much less spectral broadening compared to the anomalous dispersion regime, even though the temporal spread is slightly less than for the 1550 nanometer pulse. This is because, in the anomalous dispersion regime, higher order soliton effects cause strong temporal compression and high peak power. This leads to intense nonlinear interactions. This doesn't happen in the normal dispersion regime because the peak power stays more moderate. It would also be interesting to see what happens with the longer input pulse, let's say 1 picosecond. We focus on the 1550 nanometer input pulse in the anomalous dispersion regime. But first we need to make a few adjustments. We extend the fiber to 5 meters to see if the broadening continues. We also need a wider temporal range, about 100 picoseconds, and to maintain a high temporal resolution, we'll increase the number of amplitudes representing a pulse. We try with 10 nanojoules and here's what we get. There isn't much spectral content at shorter wavelengths, and the spectrogram shows a sequence of solitons at different positions. So we try with 50 nanojoules and reduce the fiber length to 1 meter, as not much broadening happened after that. Now we get a rather large spectral broadening. The spectrogram shows improved spectral content at shorter wavelengths. Interestingly, there seems to be a correlation between the long wavelength blobs, the soliton pulses, and the more complex short wavelength features, which don't propagate as solitons in the normal dispersion regime. We've seen how quick and easy it is to run through multiple input pulse parameters. especially wavelength, in different dispersion regimes, and seen how sensitive supercontinuum generation is to these parameters. Ultimately, tools like RP fiber power allow us to gain insights and develop better intuition about fibers. This would be very difficult to do through trial and error in a lab. In the end, we come out not only with a good design, but a better understanding of our system. To learn more about what our software can do for you, visit our website and click on the Software tab. For more case studies like these, click on the Case Studies and Tutorial button under the Encyclopedia tab. Thanks for watching, and please feel free to reach out with any questions.